Hello students, welcome to lecture 12 of the online course on Nanophotonics, Plasmonics and Metamaterials. In this lecture we will be covering dispersion relation and photonic band structure. So here is the lecture outline. So we will introduce the eigenvalue problem on dispersion relation and block modes. Then we will discuss the matrix optics approach for solving eigenvalue problem and obtaining the block modes. We will also see how to obtain the dispersion relation, calculating photonic band structure and obtaining phase and group velocities. So, eigenvalue problem and dispersion relation. If you remember from the previous lecture that till now we have established the mathematical form of the block modes as imposed by the translational symmetry of the periodic medium. So, we were considering periodic medium where the refractive index periodically alters, and these are the block modes, okay, and this is the typical 1D periodic medium we have discussed in the previous lecture. We have also seen that for this 1D periodic medium we are able to find dispersion relation. Dispersion relation, in brief, we can say it's basically omega k relation, and in this particular case we were also able to see that certain frequencies were not allowed to propagate. So, those actually gave you band gap 1, band gap 2 and so on. So, our objective here is to know how do we go to this particular dispersion relation starting from a 1D periodic medium. So, our objective here would be to solve the eigenvalue problem described by the generalized Helmholtz equation for this 1D periodic system. So, for this there are two approaches, one is Fourier optics, another is matrix optics. So, the first approach, let us have a quick look, that is called Fourier optics. Now, this approach is based on expanding the periodic function, say eta of z of the medium, okay, or you can say nz, eta is the impedance, or you can also talk in terms of refractive index, okay, and the periodic function pkz of the block mode. So, you have to expand this in Fourier series, okay, and then you convert the Helmholtz differential equation into a set of algebraic equation cast in the form of matrix eigenvalue problem, and this you have to solve numerically. So, that is what is known as the Fourier optics method. The other method is called matrix optics. So, in this case, this particular method is applicable to layered, which are basically piecewise homogeneous, like the previous example we have taken, periodic alteration of refractive index, say dielectric 1, 2, 1, 2, 1, 2 and so on, okay. And if you have those kind of layered media with planar boundaries, you are able to use matrix optics method. Now, in this particular method, instead of solving the Helmholtz equation, we make direct use of the laws of propagation, reflection and refraction, that is more or less the transfer matrix formulation that you have studied couple of lectures back. So, you can use those laws of propagation, reflection, refraction at the boundaries, okay, which are basically the known consequences of the Maxwell's equation, and then you can use the matrix methods developed for multilayer media, right. So, when you apply matrix optics method, finally you will get a 2 by 2 matrix eigenvalue problem from which you can obtain the dispersion relation and the block modes. So, we will be mainly covering this particular matrix optics approach in this lecture and in this course, of course. So, let us look into matrix optics approach. The complex amplitude of the forward and backward waves through the boundaries of multilayered medium is facilitated by the use of matrix method, something like this. So, here you can take an example of multilayered media, medium 1, 2, 3, 4 and so on. So, just to make you understand how complex the system could be. So, you start with one particular wave that is partially getting reflected, some part is getting refracted or transmitted. Now this light, when it is in this particular medium, when it hits this particular interface between this medium and this medium, some part of this light is getting partially reflected, remaining is getting transmitted. And again this transmitted light, when it encounters this particular interface, some part is getting reflected back, some is getting transmitted. Now what happens to this reflection? This is basically a backward propagating light or wave. So here again at this interface it has got two options, one is to transmit, one is to reflect, and so on. So this is how things happen, in a multi-layered medium. So you start with the single wave, but because of these boundaries you end up with getting numerous transmitted and reflected light beams. Now in part B, this particular figure, what is shown is that in each layer the forward moving waves can be named as plus, and the backward ones can be denoted using this minus symbol. So when you are in, say, medium 1, you can say that it has got a, all the forward moving waves can be summed up together, that can be called as U1 plus, and all the backward propagating waves, means all these reflections, they can be summed up together or collected together, and you can call them as U1 minus. Same in layer 2, you can have U2 plus and U2 minus. Here you can have, this is the incident medium and this is the final transmitted medium. So we are just, these are the two layers that actually form this multi-layered system in this case. Now there is a way this U1 plus and U1 minus are kind of correlated. So the amplitudes of this forward and backward collected waves, they can be represented using a column matrix. So if you actually consider this particular layer by a matrix M, so what you see here is that there is an incoming wave, there is a backward propagating wave, and there is a forward and again backward propagating wave. So you can actually represent this interface using this matrix M. Okay, so this is the column matrix. So let's correlate the coefficients. So you can have on the right side you have U2 plus, U2 minus, and this M matrix can have 4 elements A, B, C, D that are correlating this amplitude to the amplitudes on the left hand side, that is U1 plus and U1 minus. Okay. So the matrix M, whose elements are A, B, C, D, this is called the wave transfer matrix, and it depends on the optical properties of the layered medium between the two planes. Okay. Now how do you apply this for a periodic media? So in a periodic media you can actually see that this a unit cell is basically repeated, right? So if you have two alternating dielectric material, say one is having high and another is having relatively low refractive index, so the periodic media will be something like high low, high low, high low, and so on. So you can actually represent each unit cell using one matrix, and then you can repeat it like this. Okay, so this is the wave transfer matrix representation of a periodic medium, right? So you can see that the periodicity is basically capital lambda. So here you can say this is m lambda and this is m plus 1 lambda. What will be this one? This is m minus 1 lambda. Like from here to here it is the period, okay, that is given by capital lambda. So between one period to the other there is a matrix that is correlating the parameters of um plus, um minus to um plus 1 plus and m plus 1 minus. So you are basically correlating the forward propagating waves and the backward propagating waves. So as you can see here, a 1D periodic medium comprises of these identical segments like MO, okay, they are called unit cells. They are repeated along one direction. In this case we have considered Z is the direction of periodicity, okay, and they are separated by period capital lambda. And unit cells contain repetition of lossless dielectric layers, or you can say these are partially reflective mirrors. Why they are called partially reflected mirrors? If you remember that any interface wherever there is a difference between the refractive indices, okay, there will be light reflection. This can also be now discussed in terms of impedance mismatch. So, if you take the impedance of the two different layers across the interface, you will see that there is some difference in the, or there is a mismatch in the impedance, and that is why you will get some reflection of the incident wave from that interface. Now, forming a symmetric system generated by a generic wave transfer matrix. So, you can actually make a generic wave transfer matrix which looks like this. What are the elements here? 1 by T conjugate, R over T, R conjugate over T conjugate, and 1 over T. So, this is how you are able to write a generic wave transfer matrix where R and T are basically the reflectance and transmittance. This you have already seen from the Fresnel equation. You know what is reflectance and transmittance. So, if you want to calculate what is, or you can, these are basically amplitude transmittance. So, small t can be called as transmission coefficient, or you can call them as amplitude transmittance. Small r can be called as reflection coefficient or amplitude reflectance. So, correspondingly you can find out what is the intensity transmittance and intensity reflectance. So, this is how you can calculate. Okay. Capital T equals modulus T square, R equals modulus small r square. So, the electromagnetic wave traveling through the medium, they will undergo numerous transmissions and reflections that we have seen in the previous slide, and that will actually give you one particular forward and one particular backward moving wave at each plane. Okay. And the transfer matrix this particular matrix method, not transfer matrix, this is called matrix optics method. This can be used to determine the block modes. So, let us assume um plus minus as the complex amplitudes. So, plus 1 correspond to the forward and minus corresponds to the backward wave at any initial position z equals m lambda. So, here this particular one. So, what is m? M is the number of the unit cell. Okay. So, the amplitudes elsewhere within the cell can be determined by a straightforward application of the appropriate wave transfer matrices as discussed in the previous lecture. So, we have seen this already, that if you know at one position, you can add that phase and you can get the amplitude at any other location. Now, the dynamics of the amplitude varies from one cell to another, which is described by the recurrence relation. That means the amplitude plus and minus, they will vary from one cell to another, but in a repeated pattern. So, what is that pattern? That is kind of like this. So, this is the initial amplitude, and you multiply it by this particular unit cell matrix, that is m0, you will get the next set of amplitude of the forward and backward moving wave. So, these relations are used to compute the complex amplitude at any particular cell if the amplitude of the previous cell are known. Make sense? These are the amplitude of the previous cell, this is the cell matrix. So, when you multiply this, you get the amplitude of the current cell. Now, let us see how do you obtain eigenvalue problem and block modes from this. So, by definition, the modes of the periodic medium are self reproducing, and why so? Because they actually maintain a particular phase relation. So, you can say that if you take the amplitude of the forward and backward moving waves for mth cell, where m is 1 or 2 or 3 or so anything. In that case, if you multiply this by e to the power minus j phi, that is the amount of phase accumulated while crossing this unit cell, you can actually get the amplitude of the forward and backward propagating waves of the next unit cell. Okay. So, here what is important, that this phi is basically the phase accumulated over the distance of the period, and the period is nothing but capital lambda. So, there is a name to this phase. So, this phase are basically altered by a common shift phi, and this phi is called as block phase. Okay. So, there is a corresponding block wave number which is defined as k, capital K, that is given by phi over capital lambda. So, obviously what is that then phi, which is block phase, phi turns out to be k capital lambda. Okay. So, this is nothing but block phase. So, finding the complex amplitudes, that is plus minus, and the phase phi, which is defined as k capital lambda, from the following equation which satisfy the self reproduction condition, can be cast as an eigenvalue problem. So, let us see how it looks like. So, if you take this particular problem where you already seen this equation, that this is the phase relationship between the amplitude of the next cell and the previous cell, and here if you put m equals 0, you get u0 plus u0 minus. Okay. And what you will have? You will have here basically u1 plus and u1 minus, right? And u1 plus and u1 minus, you can go back, and from here you can get that u1 plus and u1 minus can be written as m0, u0 plus and u0 minus, right? So, if you bring this equation here, so on the left hand side you get m0, u0 plus u0 minus is equal to e to the power minus j phi u0 plus u0 minus. So, this is an eigenvalue problem of this 2 by 2 unit cell matrix M0, right. So, here if you look into this particular equation, this is your eigenvalue. So, the factor e to the power minus j phi is the eigenvalue, okay, and the vector with components u0 plus and u0 minus are basically the eigenvector, right. So, how do you obtain the eigenvalues? The eigenvalues are basically obtained by equating the determinant of the matrix, that is M0 minus e to the power minus j phi times identity matrix. If you take this determinant and equate it to 0, you will get the values at which you will get those solutions are basically the eigenvalues. Okay. Now, we already know that these are non-absorbing material. So, amplitude transmission coefficient square plus square of the amplitude reflection coefficient square is equal to 1. In that case, you can actually find out the values, which is e to the power minus j phi, okay, can be given as this quantity. So, you have this transmission coefficient, also its conjugate, and this is the value that you obtain. And from this you can write that if you separate it out to the real and imaginary part on both sides, you can find that cos phi can be written as real of 1 over the amplitude transmission coefficient. So, real of 1 over t. So, keep this equation in mind. So, now let us try to obtain what is the dispersion relationship. Always remember, dispersion relationship is basically the relationship between the block wave number k and the angular frequency omega. That is, we are looking for omega k relationship. Okay. So, the previous equation that you have seen, this one, this equation. So, this equation provides the eigenvalues which is exponential minus j phi of the unit cell matrix, and this is basically the progenitor or the source of the dispersion relation for the 1D periodic medium. So, how it works? So, we already know that phi, that is the phase, can be given as capital K, that is the block wave number, times the period. So, phi phase is basically proportional to K, okay, and T, the transmission, is also associated with frequency. At different wavelength or frequency, you will have different transmission. So, T can be written as T omega, right. So, these two are related through the phase delay associated with the propagation through the unit cell. So, you can actually write that cos 2 pi k over g times phi is nothing but real of 1 over t, which is a function of omega. So, this one directly correlates your k and omega, and hence it can be named as dispersion relation. Now, the question arises, what is g here? G is basically the fundamental spatial frequency of the periodic medium. So, what is the period? Period is capital lambda. So, g will be 2 pi over capital lambda, right. So, this particular function that you see here on the left side, cos 2 pi k over g, is nothing but a periodic function of this k, which has got a period of g, okay. So, g is nothing but 2 pi over capital lambda, and this gives multiple solutions for this equation for any given omega, okay, and that is how you are able to obtain that dispersion relation, which is typically shown as in the photonic band diagram. Now, but the solutions separated by the period g, they are not independent. They basically lead to identical block modes. So, the domain of the dispersion relation is typically limited with the values of k ranging from interval of minus g by 2 to g by 2. That means, it is basically ranging from minus pi by capital lambda to plus pi by capital lambda, which is nothing but the Brillouin zone. So, that is why the concept of Brillouin zone comes from, and that allows your phase, okay, phi, to be limited to an interval of minus pi to pi. So, once you know the phase variation from minus pi to pi, you are basically covering the entire 2 pi, right. So, after that it is just a repetition. So, there is no point computing those, okay. So, this range, this interval can give you the interval of phase starting from minus pi to pi. Also, we need to keep in mind that this cos function is an even function of k. So, for each value of omega, there are two possible values of k, okay, two independent values, and they could be equal in magnitude but opposite in sign within the same Brillouin zone, okay, or within the Brillouin zone. So, Brillouin zone is from minus pi to pi in terms of phase, or you can say it is from minus g by 2 to g by 2 in terms of k. So, this actually gives us that they are independent block waves. So, one solution is for forward propagating wave, another solution is for the backward waves. So, dispersion relation gives you the photonic band structure. So, for dispersion relation will also tell you the multiple spectral bands, which can be typically classified into two regions or two regimes. So, one is propagation regime. So, spectral band within which capital K, that is the block wave number, is real, those are the propagating modes. So, in those cases, the real part of 1 over t, which is a function of omega, okay, that is less than 1, and these bands can be numbered as 1, 2 and so on, starting from the lowest. Makes sense? And there could be other cases where in some spectral bands this k is complex. That means they correspond to evanescent waves. Okay? It means these waves will get rapidly attenuated and they cannot propagate within that periodic medium. So, in this case, if you see, they will give you, okay, ignore this particular sign, it is only modulus of real 1 over t, and that will come out to be greater than 1. And these bands behave as stop bands, okay, of the diffraction grating. So, they are also called as photonic band gap, PBG, or forbidden band gap, since no existing propagation mode are possible in this particular case. So, now let us look into the calculation of photonic band structure by taking an example of periodic stack of partially reflective mirrors. So, here is a stack of periodic stack, you should say, of partially reflective mirror, and the wave travelling along the axis of the periodic stack is in the direction of z. What is the period here? Capital lambda. Now, let us see how we actually characterize this. So, the dispersion relation for a wave travelling along the axis of the periodic stack of identical, that is very important, identical partially reflective lossless mirrors which are separated by capital lambda. So, in this case the power reflectance is modulus of r square and intensity transmittance is nothing but what is not reflected is getting transmitted, because these are non-absorbing case. So, you can say modulus of t square, that is transmittance, is nothing but 1 minus modulus of small r square. Now, let us use the matrix optics approach to derive explicit expression for elements of the scattering matrix of the composite system in terms of the elements of the scattering matrix of the constituent system. That is, we will take the elements of the unit cell and we will try to get the matrix elements for the overall system. So, the matrix M whose elements are say A, B, C, D, you can call them as wave transfer matrix, which we have seen in this particular equation. So, they depend on the optical properties of the layered media between the two planes, right. So, we have already seen this particular case that you can obtain those equations or those elements from Fresnel reflection coefficients. An alternative to the wave transfer matrix that relates the 4 complex amplitude of the at the two edges of layered medium is a scattering matrix S matrix. So, you can also have S matrix, and S matrix are more popularly used in describing transmission lines, microwave circuits and scattering systems. Okay. So, in this case the outgoing waves are basically expressed in terms of incoming waves, something like this. So, S matrix is used to describe transmission lines, microwave circuits and scattering systems. So, in this case the outgoing waves are basically expressed in terms of the incoming waves. So, here is a schematic representation of S matrix. So, you see that you have the incoming wave U1 plus and you have one outgoing wave, that is U2 plus. Now, in this case this is a reflection, but you are actually trying to represent it in terms of outgoing wave, because the reflection is also outgoing. So, you put it on the right side. So, you call it as U1 minus, and the reflection from the other side becomes kind of incoming wave. So, you can actually take that U2 minus, okay, as a incoming one. So, in that case you can simply see that what are the two outgoing outgoing waves from this particular system, that is U2 plus and U1 minus. So, U2 plus and U1 minus are the outgoing, and what are the incoming? U1 plus and U2 minus. So, U1 plus and U2 minus, and you are trying to correlate this outgoing set of waves with the incoming set of waves. So, what are the coefficients? So, U2 plus, as you know, U2 plus will be nothing but U1 plus times the transmission, that is T12. So, T12 times U1 plus. Okay. Also, it will have another component coming from this one. So, whatever is this wave, whatever is getting reflected, that will also contribute to U2 plus. So, you can have, this is 2, this is 1. So, you can, this reflection coefficient will be called R21. So, you will have R21 times U2 minus. Is it clear? So, you will have U2 plus, that is given as T12 times U1 plus. So, T12 times U1 plus, this one. So, there is also one contribution coming from this one, some part of it will get reflected and add up to this outgoing wave. So, that will be R21 times U2 minus. The other one also you can easily make it. So, this one U1 minus is nothing but R12 U1 plus. So, whatever is incidenting, some part is getting reflected. So, that reflection is this one R12 U1 plus, and then whatever you are putting here, some part is getting transmitted, and that also comes back as U1 minus. So, that is T21 times U2 minus. So, this equation U1 minus is nothing but R12 U1 plus plus T21 U2 minus. Clear? So, unlike the wave transfer matrix, these elements here in scattering matrix, they have direct physical significance. Something like, if you take R12 and R21, they are basically the forward amplitude transmittance and reflection. That is, they are basically the transmittance and reflection coefficient of the wave incident from the left side. On the other hand, if you see T21 and T21 and R21, they are basically amplitude transmittance and reflectance in the backward direction, that is for wave that is coming from the right side. So, it is easy to correlate physically what is happening in the case of S matrix. Now, for a homogeneous layer of width d, so this interface we have seen that what happens with the incoming and outgoing, or you can say what is falling, getting reflected, and so on. So, for a homogeneous layer of width d and refractive index n, that is shown here, the complex amplitudes of the collected waves at the planes indicated by the arrow. So, if you are looking about the complex amplitude at this particular planes, so you can call this as U1. Okay. So, this is U1, forward one will be U1 plus, backward one will be U1 minus, this will be U2. Okay, the amplitudes here will be U2, the forward one will be U2 plus, and the reverse one will be U2 minus. So, how they are related? They are propagating, or they are traveling this particular distance. So, they will add up a phase. So, U2 plus will be simply U1 plus times e to the power minus j phi. What is phi? Phi will be n k naught, small k naught, and d. Okay, n is the refractive index, k naught is the free space wave vector or wave number, and d is the thickness of that layer. So, that is similarly you can also correlate what is U1 minus and U2 minus. So, that is how you can obtain the wave transfer matrix as well as scattering matrix for this particular case. So, if you see that wave transfer matrix M will look like exponential minus j phi 0 0 exponential plus j phi, whereas the scattering matrix, because scattering matrix will try to represent all outgoing in terms of incoming, not left and right. Okay. So, it will look like e to the power minus j phi 0 0 e to the power minus j phi. Okay. So, that is the only difference between the wave matrix or wave transfer matrix and scattering matrix. So, now let us consider a wave transmitted through a system which is described by S matrix, which has got these elements T12, T21, R12, R21. So, these are easy to handle because we already know this transmission and reflection coefficient from the Fresnel equation. So, let us assume that this system has got two such separate systems, okay, and these are the S matrix for these two separate systems. So, by multiplying the two associated M matrix, so you can convert this into M matrix, this one into M matrix, you can multiply the M matrix and then convert it back to the scattering matrices, okay, and you will be able to obtain the overall transmittance and reflection. So, overall transmittance in this case will be T13, which is given by T12, T23, okay, over 1 plus R12, R3. So, this is how you will be analyzing the multi-layer system. Okay, you can also find out what is the reflection coefficient for this overall system. Okay. So, one important thing is that the relationship between M and S matrix in this case. So, as I mentioned, M matrix are having 4 elements A, B, C, D, and they are not directly the reflection and transmission coefficient, whereas the S matrix are directly the reflection and transmission coefficient. So, sometimes it is easy to deal with S matrices. Okay. Now, in this particular case, the transmission of a plane wave through a cascade of two separate systems that we have seen, which are separated by a distance of d. Okay. Now, we have assumed that if the two cascaded systems are mediated by propagation through a homogeneous medium, it means the medium in between is a homogeneous medium, then the overall transmittance and reflectance will also have this extra factor adding up, that is exponential minus j phi, and phi is nothing but n k naught d. Okay. So, that way the equations will also get slightly modified. Okay. So, as I mentioned here, the phase phi is nothing but n k naught d, and d is the propagation distance, n is nothing but the refractive index of this particular medium inside. So, with that, what we learned is that we understood the overall reflectance and transmittance, and for this periodic stack of identical partially reflective lossless mirrors, okay, using the equations this and this, you can obtain what is the dispersion relation, or you can find out that cos of 2 pi k by g is nothing but 1 over mod t cos omega over omega b. So, here a new term omega b has come. So, omega b, so g you already know, g is 2 pi by capital lambda, that is the spatial frequency, spatial space related. So, spatial frequency, and that you have omega b, which is c pi by capital lambda. So, this is particularly a plot of the dispersion relation for a set of periodic mirrors. So, here certain values have been assumed, like modulus t square has been taken as 0.5, and they have been considered to have a separation of capital lambda. Omega b is c pi by capital lambda, g is 2 pi by capital lambda, those are all fine. So, only important thing is the value of t is already assumed here. and you can see this red dotted straight lines, they are basically the approximation of a homogeneous medium. So, if you assume the entire medium to be homogeneous, in which omega by k equals c, okay, or you can carefully work this out and see that omega by k will be omega b times g by 2, that also comes out to be c. So, you will have this straight lines. Okay. So, these are basically the homogeneous medium approximation. So, what it tells you that, this graph tells you that because of the periodicity, how much the dispersion relation deviates from the homogeneous medium. And in homogeneous medium, you see there is no band gap also. So, all the bands are allowed. All the bands are allowed means all the frequencies have some k vector. It means at all frequencies you have solution for waves which has got real propagation constants. Okay. But here in this case you can see it starts with a band gap, then there is some band which is allowed, then again there is a band gap, then again there is some band where the propagation is allowed, then again there is a band gap, and so on. Okay. Now, this is what I have already discussed, that here the photonic band gaps, there is no real solution, so you do not have anything, and all the band gap frequencies are basically centered around omega, or you say omega b, 2 omega b, and so on, 3 omega b. So, the frequencies, these particular frequencies, they do not permit any propagating mode. Rather, in that case, if the wave is not allowed to propagate inside the periodic medium, what will happen? In terms of reflectance, you will see that they have unity reflectance. And this is a particular system where you also see that the lowest photonic band gap is at omega equals 0. So, if you take a real example with some values like n1 equals 1.5 and n2 equals 3.5 and keep the thickness of the two layers similar. So, this is one layer, this is another layer, and then you are repeating this unit cell. So, this is the period, okay, period of the unit cell. So, if you take this and you try to calculate the dispersion relation, you will see that the photonic band gaps have center frequencies at omega b here also, omega b and its multiples like omega b, 2b, 3b, and so on, and they occur at either the Brillouin zone center, that is k equals 0, or at the edges, that is k equals plus minus g by 2. So, this is the range of the Brillouin zone. So, k value starts from minus g by 2 to g by 2 as we discussed before. So, here you see that initially all frequencies are permitted. At omega b you have a particular band gap, again at 2 omega b you have a band gap, and so on. Okay. And this is how it deviates from the homogeneous medium approximation. So, these are the values associated with this particular band gap. Now, in this setup of partially reflective mirrors, the frequency region surrounding to omega equals 0 does not fall in the band gap. It has got some solution. So, it is good. In this case, there are some propagating modes possible here. Okay. Now, dielectric materials with lower contrast, they will have band gaps of smaller width. Now, here you see the contrast is really good. So, N1 is 1.5, N2 is 3.5. Now, if you take two material where the difference between N1 and N2, like you can say delta N is less, this band gap will also become very narrow. Okay. So, if you want a larger band gap, you choose two materials which have higher contrast between them. Okay. And this red straight lines we already mentioned that this is how light would have behaved if we have a homogeneous medium with refractive index of the mean of N1 and N2. Fine. So, from this you also can derive the information about the phase and group velocities. So, the propagation constant capital K, it correlates to the phase velocity as well. So phase velocity will be omega over capital K. So once you know the phase velocity, you can also find out what is the effective refractive index, that is small n effective, okay, that is C naught over the phase velocity. So you will get C naught capital K over omega, fine. So this is, we are taking only up to this one. So here you can see that, clearly see what is the photonic band gap, okay, and this is the plot of effective refractive index, that is C naught K over omega, okay. So that is basically the effective refractive index. We can also find out what is the group velocity, that is V equals d omega by dk, okay, which corresponds to the pulse propagation in the medium. So any pulse will have a frequency spread, okay, means it will not be monochromatic, it will have certain frequencies. So you should calculate the group velocity in that case. So group velocity should be obtained by d omega by dk. So accordingly you can also find out what is the effective index seen by that group, or you can call it effective group index, that is also defined as capital N effective, and that can be given as C naught over this V. So you get C naught d omega dk by d omega, okay. Now these velocities can be calculated at any point of the dispersion relation curve by deriving the slope d omega by dk, and you can also take the ratio of omega by k. So as shown here, you can calculate what is small n effective, what is your capital N effective, what is n bar. N bar, this is the mean value, okay, mean refractive index. So the figure here, the first one shows the dispersion relation of a alternating layer of dielectric medium, and this two shows the effective index of one particular frequency, and this is the group index, okay. So here what you see, you are able to clearly see two frequency bands where the propagation is possible, and there is a definite photonic band gap, okay. And for lower frequencies within the first photonic band, you can see that this is how the effective index is. So you can say that N effective is very close to the average effective index. So initially this dotted line and this blue line, they are very much overlapping, okay. So here also you see they are very much overlapping, but as you keep on going further, okay, with omega, or you can say with wavelength, it is expected that at longer wavelength the material becomes homogeneous. So K is reducing, means wavelength will be increasing. So this is the case where you see more homogenized picture of your periodic medium. But as K is increasing, your wavelength is basically reducing. So you will be able to see the definite structures, and that is where you will be deviating from the line, this particular red dotted line, which represents a homogenized medium, okay. So here also you can see with frequency increase, so this way the frequency is increasing, okay, this way the frequency is increasing. So it's better to correlate with frequency and wavelength, and this is the spatial period, okay. So you can correlate with the frequency here, that at lower frequency wavelengths are high, so you are seeing much homogeneous picture, whereas when you go for higher frequency, you have lower wavelength, you start deviating from the mean refractive index, okay. That is the crux of this particular thing. And at the bottom of the second band, that is here, you will see that the N effective is much smaller than the mean refractive index. So that is how it works, that with the frequency increase, initially N effective goes way above the mean value, but then suddenly it encounters a band gap, and after the band gap, at the bottom of the second band you will see that the N effective starts from a value which is much slower or much smaller than the mean refractive index. So, N effective increases at higher frequencies and with approaching to N bar, which is the mean value at the middle of the band. Understood? Now, this drop of N effective from a value above average, which is just below the band gap, to a value which is below average just above the band gap, is due to the significantly different spatial distribution of the corresponding block modes. So, there is a band gap, because of which the block modes which are propagating here and here are significantly different. So, we do not expect them to have similar kind of feature, and that is why there is a drastic change in this effective refractive index as well. And these block modes are orthogonal to each other. So, there is no similarity basically between these block modes. Now, the block modes at the top of the lower band has greater energy in the dielectric layers with higher refractive index, so that the effective index is basically greater than the average. And if you look into the block modes at the bottom of the upper band, it will be reverse. It means in that case greater energy is localized in the layers which are having lower refractive index, and that is why the overall effective index is lower than the average. So, these are like two different mode configuration for the two different block modes which is present here and here. Fine. Lastly, let us also look into the frequency dependence of the capital N effective, which is the group effective index, and you see the group effective index increases at the edges of the band gap, either from below or above. Okay, in both cases it is behaving the same way, and that means the group velocity is much smaller. So, when index is larger, the group velocity is smaller. It means when you are approaching a band gap, you will see that the waves are much slower. So, the optical pulses are significantly slow near band gap's edge. So, that way you can actually make different devices based on this particular concept. So, with that we will stop here today. Thank you. Any questions, you can drop an email to this particular email address, and we will see you in the next lecture. Bye.